Hi class, in this recording we are going to dive into air. What is air and what is it made of? So as we look at air on planet Earth, it's a nice blend, a wonderful cocktail of nitrogen, mostly nitrogen, a little bit of oxygen, and then some carbon dioxide, and then miscellaneous stuff like water vapor, depending on temp and humidity, and then a lot of minor gases. So I really want to emphasize we have mostly nitrogen, then a good chunk of oxygen, and a little bit of water and carbon dioxide. Those are some big important things here as we look at the composition of air. Overwhelmingly nitrogen, then oxygen with a smidgen, a squish of carbon dioxide. And we take all these different gases that are in our air and we can have partial pressures from individual gases. And this is kind of overwhelming. Let me back up a slide here. This looks a lot like math from chemistry. Ooh. So as we look here, here's a nice happy pie chart. And let's say all of these different gases represented over here represent one atmosphere. Oh, get over here. Now I can keep writing. 1 atmosphere of pressure. This would mean that from nitrogen, since the atmosphere is 78% nitrogen, that 1 atmosphere of pressure would be, from nitrogen, would be 0.78 atmospheres of pressure from nitrogen. That's how much atmospheric pressure is from that specific gas. Oxygen is 0.209%, or 0.0, I'm misspeaking here. If we look at the pressure of oxygen, it's 0.209 atmospheres, ATM, of pressure from the oxygen. So as we look at gases as a whole, the overall pressure of a gas is going to be equal to and correspond to the individual pressures of the individual gases all added up that make that cocktail or the total mixture that we're looking at. So let's jump ahead then to Dalton's law of partial pressures. So if we look at atmospheric air, our air is 78% nitrogen. And if we take 1 atmosphere in millimeters of mercury, 78% multiplied by 760 millimeters of mercury gives us 597 millimeters of mercury. So this is the pressure in our atmosphere due to nitrogen gas. That's the partial pressure of nitrogen. And then if we take 20% oxygen multiplied by atmospheric pressure, we get pressure from oxygen gas. And we can do the same for water and carbon dioxide. And then we take all those individual partial pressures of the individual gases and add them all together to get the total pressure of the gas that we're looking at. So Dalton's law of partial pressures is when we sum the pressure contributions from individual gases. And I remember as a freshman in college, this particular idea really made my brain hurt. So, if you have a bit of a headache right now, you're in really good company. But try not to make it more complicated than it needs to be. We're not going to be doing any partial pressure calculations in lecture or lab for that matter. I just wanted to illustrate this idea because on subsequent slides, we talk about partial pressures of gases in the bloodstream. So as we look at our air on the inside of our alveoli is going to be different from the air that we breathe in versus the air that we breathe out. So inspired air, which is also atmospheric air, and alveolar air that's been in our alveoli for a while, are going to be different from each other. And there's key differences that occur. First, as atmospheric air goes into our lungs, we humidify it. So the alveolar air is going to have a higher partial pressure of water, which is just a nice way of saying that there's more water in the air of our lungs. It's really humid. And now we've described that idea with partial pressures. And let's think of the air in our alveoli. Our bloodstream is constantly pulling oxygen out and adding carbon dioxide to the air in our alveoli. So the air in the alveoli is going to have a lower partial pressure of oxygen and a higher partial pressure of carbon dioxide. And this means that the air in our alveoli and the residual left over from the previous respiratory cycles are going to have varying compositions. And then the alveolar air itself, because it's constantly exchanging oxygen with the blood to change its composition, means that the partial pressure of oxygen in alveolar air is less. It's only 65% of that of inspired air. Another way to phrase this is atmospheric air has a more oxygen than alveolar air, or alveolar air has 45% less oxygen than atmospheric air. And then when we look at carbon dioxide, the partial pressure of carbon dioxide is 130 times higher in our alveoli, or in the alveolar air, compared to atmospheric air. So we have lots and lots of carbon dioxide in our lungs, in our alveolar air, relative to the external atmosphere. And during these gas exchanges, during alveolar gas exchange, we have oxygen and carbon dioxide swapping across that respiratory membrane, made of the alveolar epithelium, a basement membrane, and then the endothelium of the capillary. And gases are always going to move with their concentration gradients to go from an area of high partial pressure to an area of low partial pressure. So because we have high PO2 in the lung alveola relative to the bloodstream, we have oxygen going this direction into the bloodstream. And because we have a high PCO2, partial pressure of carbon dioxide in the blood, carbon dioxide tends to move into the alveoli through simple diffusion. So the individual gases move relative to their individual partial pressures. Now within our alveoli, we have blood unloading carbon dioxide and loading up oxygen. And this all is going to involve our red blood cells, our erythrocytes. The efficiency of this process depends on a couple things. How efficiently we can have loading and unloading of these gases. We need to influence how long the red blood cell stays in the alveolar capillaries. We need at least a quarter second for equilibrium. However, when we're at rest, our red blood cells spend 3/4 of a second in the alveolar blood capillaries. So they can absolutely achieve equilibrium with our gas exchanges. During strenuous exercise, our red blood cells will spend 3/10 of a second in the alveolar capillaries, which is enough to achieve equilibrium, but it's really cutting it close. And I know I said this on the previous slide, but I'm going to say it again. Our carbon dioxide and oxygen each behave independently of each other. One gas does not influence the other gas. So as we look at these pressure gradients, if we have 104 millimeters of mercury worth of oxygen in alveolar air versus the partial pressure at 40 millimeters of mercury in our blood, that means that we'll have oxygen gas go from the alveola into the bloodstream. And to put some numbers to it, we typically are going to have approximately 46 millimeters of mercury of carbon dioxide in the blood versus 44 millimeters of mercury of oxygen, carbon dioxide in the alveolar air, which is to say we have more carbon dioxide in the blood than the alveola, so we have a net movement of carbon dioxide from the blood into the alveola. And as we're looking at these pressure gradients of gases, these are our typical, or stereotypical pressure gradients. We can introduce something called hyperbaric oxygen therapy when we give somebody elevated atmospheric pressures of oxygen. So when we give them oxygen at greater than 1 atmosphere of pressure, this is going to increase the pressure gradient of oxygen. That's going to force more oxygen into the bloodstream. And this is done to treat conditions like gangrene, when we have tissue dying due to low oxygen concentrations in the blood, or carbon monoxide poisoning, not dioxide, but monoxide. Carbon monoxide poisoning is oftentimes going to be treated with hyperbaric oxygen therapy. So if we look at up here, the pressure of oxygen in a hyperbaric oxygen chamber is approximately, I'm going to guesstimate about 2,000 millimeters of mercury. And then if we look at venous blood in the lungs, it's down here. So we have a very steep gradient. So oxygen moves into the blood very rapidly, very quickly. This blue line represents normal air pressure. So we can have a normal movement of oxygen into the bloodstream. And then if you're at a high elevation where there's low oxygen concentrations, you have less oxygen in the atmosphere, the oxygen gradient is shallower, and less oxygen goes into the bloodstream, or it takes longer for the oxygen to go into the bloodstream. And that's something that occurs at high altitude. It's because we have that lower gradient. Now, as we look at these gases that we're trying to get into our blood, we have to look at the solubility of the gases. Carbon dioxide itself is very soluble, 20 times approximately more soluble than oxygen gas. This is one of the reasons why we make carbonated beverages like carbonated soda pop as opposed to oxygenated beverages. Like it's just easier to dissolve carbon dioxide in water than oxygen. So as we look at the amount of oxygen and carbon dioxide that are exchanged, if we have equal amounts being exchanged, that carbon dioxide is going to be much more soluble and diffuse much more rapidly into the water that makes up the solution. Another thing that's going to influence the rate of exchange is how thick the membrane is. Our respiratory membrane is approximately half a micron thick, or 0.0000 milliliters thick. So it's really, really, really thin. Things that can cause our respiratory membrane to be thicker include pneumonia or edema. So if somebody has a pneumonia, they are going to have some fluids building up in the alveoli, causing the individual to have a thicker respiratory membrane. And if somebody has edema, the simple squamous epithelium, the respiratory membrane itself swells up, and that makes it more difficult to get the oxygen into the bloodstream. And then something else that is going to influence the rate of gas exchange is surface area. The higher the surface area, the higher the rate of diffusion. So if we look at our blood capillary, or alveola, we have those alveola spread over approximately, or our alveola make up approximately 70 square meters. So we have 100 milliliters of blood spread out over 70 square meters. That's like taking about a third of a cup of water and spreading it out over a bedroom floor, or typical bedroom floor. Think of like a 13 by 13 foot bedroom. Don't double check the measurements. I just made up those numbers right now. An average size bedroom. Now, as we look at our surface area, things that can reduce the surface area of our lungs include emphysema, which is shown here in this figure, where we have degradation of the respiratory membrane. Adjacent alveolus will merge with each other. We can have lung cancer or tuberculosis as well, decreased surface area within our lungs. And this will be our last slide for this recording. We're going to camp on this one for a while. With ventilation perfusion coupling, we are going to always pair the amount of blood flow in and out of the lungs with the amount of airflow in and out of the lungs. In a nutshell, blood flow will always match airflow and vice versa within our lungs. Ventilation perfusion coupling. They're linked or coupled with each other. So let's say we have a decrease in airflow. If we have that decrease in airflow, that's going to make it so we have less oxygen in our blood vessels, and less oxygen is going to cause vasoconstriction of the pulmonary vessels. So, and if we have vasoconstriction of pulmonary vessels, we have less blood flow in the lungs, so that the blood spends more time at the alveola and can absorb more oxygen, which will ultimately make it so that we have the oxygen levels go back up again. We can maintain homeostasis. Let's say we have increased airflow. If we have increased airflow, that's going to cause elevated oxygen within the blood, elevated oxygen causes vasodilation of the pulmonary blood vessels. That causes more blood to flow more rapidly across the alveolar capillaries. So the blood will spend less time exchanging gas at the alveola, and that's going to result in ultimately less oxygen in the blood. So we'll have the blood flow matching the airflow. Let's say we have decreased blood flow. So now we're going to look at the same thing, but a different way. If we decrease the flow rate of blood, that's going to reduce the amount of carbon dioxide in the blood because the blood has more time to exchange gas at the alveoli and get rid of carbon dioxide. And as we reduce blood carbon dioxide levels, we have constriction of our bronchioles in our lungs. Constriction of our bronchioles makes it so that we breathe in and out slower. We have decreased airflow. And that decreased airflow is going to ultimately increase blood carbon dioxide levels, offsetting the initial stimulus. So we have another negative feedback loop right here. And then here, let's look on this loop right here. If we increase blood flow in our lungs, that means that we're going to get rid of too much carbon dioxide, and then our blood carbon dioxide levels, excuse me, that means that we do not get rid of enough carbon dioxide. We have elevated carbon dioxide. And if we have elevated blood carbon dioxide, our blood becomes too acidic. That leads to dilation of the bronchioles, which is going to cause increased airflow so we can exhale carbon dioxide faster. And the faster we exhale carbon dioxide, the more we will lower that elevated level of carbon dioxide in the blood, ultimately restoring homeostasis. So we just talked about 4 negative feedback loops on this slide, about how blood flow and airflow will constantly adjust to each other. And if one decreases, the other may decrease, or if one is decreased, the other will decrease as well. So we compare a decrease of airflow with a decrease in blood flow. A decrease in blood flow is paired with a decrease in airflow. So when one goes down, the other goes down. If we increase blood flow, we increase airflow, or if we increase airflow, we increase blood flow. That's another way to look at these relationships. If one goes up, the other goes up. Now, if you have any questions or comments about this material, please post them on the class discussion boards or shoot me an email. And as always, happy studies.